Hello! Today we're diving deep into how blockchain technology works. While many associate blockchain with cryptocurrency trading, this video focuses on the technology behind cryptocurrencies, not trading advice or market analysis. While the concepts can seem complex and the jargon overwhelming, this guide will simplify everything and fast-track your understanding. Let's explore how this transformative technology works and why it matters. The term blockchain gives away its structure. It's literally a chain of blocks. Each block is like a container that holds data, often a collection of transactions. These blocks are linked together in a sequence, forming a chain where each block references the one before it by including a unique identifier called a cryptographic hash. Think of a hash as a digital fingerprint of a block's content. Like a fingerprint represents the whole particular human body, a hash, which consists of a line of symbols, represents some data of any size. If anything in a block changes, its hash also changes. This ensures that any given piece of data will always result in the same hash, making the blockchain predictable and consistent. These cryptographic hash functions are special types of hashing methods with the following properties. Same input always produces the same output. Quickly generates hashes. Hard to reverse engineer the input from the hash. Difficult to find two different inputs with the same hash. Computationally infeasible to figure out the input from the output. Cryptographic hash functions are used in every part of the blockchain and are playing a crucial role, linking blocks together, securing transaction data, ensuring the integrity of the blockchain. This ensures that every block in the chain is securely connected to its predecessor, making the entire chain tamper-proof. The first block in the chain is called the genesis block or block 0, and it's unique because it has no previous hash to reference. Instead, it might contain hard-coded data or initial state information necessary for the blockchain to start. Blocks exist to group and organize transactions. Each transaction represents an agreement between two or more parties and is securely validated and stored on the blockchain ledger. It's like sending a package through a secure courier service. The sender packs the contents, which is cryptocurrency or data in blockchain, signs it to prove it's from him, the sender. The courier, minus validators, checks and delivers it to the recipient. And this entire process is recorded in a secure, unchangeable ledger blockchain. So each block holds a digest, its own hash, and reference to the previous block's hash. Inside the block, you'll find a batch of transactions, which could include things like payments or data updates. For example, in the Genesis block, block 0, account A starts with 100,000 tokens. In block 1, account A transfers 10 tokens to account B. This transaction is validated by checking the balance in block 0, ensuring account A had enough tokens to make this transaction. This verification process involves following the chain from the Genesis block forward, checking each transaction's validity against the state of previous blocks. This not only verifies transactions, but also ensures the integrity of the entire history of the blockchain. The immutability of blockchain stems from this chaining mechanism. Altering a transaction in any block would change its hash, which in turn would mismatch with the hash stored in the subsequent block, breaking the chain. In a decentralized world, this would require control over more than half of the network's computing power to rewrite history, which is typically impractical. Just like no two fingerprints are the same, ideally, no two pieces of data should result in the same hash due to the properties of hash functions. This structure creates an unbroken, verifiable history of all transactions in the blockchain. Since every block relies on the data in the previous one, altering any block would require changing every subsequent block, which is nearly impossible in a decentralized system. The structure, where each block must contain a valid reference to the previous block's hash, is maintained through consensus mechanisms, ensuring all participants or nodes agree on the state of the blockchain. This is critical because blockchains are decentralized. There's no central authority to validate transactions or maintain the ledger. Instead, consensus mechanisms enable the network to operate securely and trustlessly. By the way, in the context of blockchain technology, the term trustless generally has a positive connotation. Participants in the network only need to trust the math and the rules of the blockchain protocol, which are transparent and verifiable by anyone. Unlike the real-world trustless person, for example, which is not a good thing, with a trustless system, security is not dependent on the honesty or reliability of a third party. Instead, it's based on cryptographic proofs and consensus mechanisms. Because all transactions are recorded on a public ledger, anyone can verify the transactions without having to trust to a third party has acted honestly. This openness leads to a system where trust is replaced by verifiable evidence. However, trustless doesn't mean no trust at all. There's still a need to trust to underlying code, the consensus mechanism, and the security of the blockchain's network. So, what is this consensus mechanism I've mentioned several times for the past 2 minutes? It's the method blockchains use to get everyone on the network to agree on which transactions are valid and should be added to the blockchain. Imagine a group of people trying to agree on the balance in a shared bank account, but no one trusts each other completely. A system is needed to ensure no one is spending money they don't have, decide the order of transactions so everyone's ledger matches, stop bad actors from altering the ledger. Consensus mechanisms solve these problems by creating rules for verifying and recording transactions in the blockchain. The process varies depending on the specific mechanism, but the general steps are as follows. A user initiates a transaction, such as sending cryptocurrency. The transactions broadcast to all nodes or computers in the network. Nodes verify the transaction to ensure it complies with the network's rules. For example, the user has sufficient balance, digital signature is valid, etc. Once enough transactions are validated, they are grouped into a block. Nodes agree on whether to add the new block to the blockchain by following the rules of the consensus mechanism. Once consensus is reached, the block is added to the blockchain and the transaction becomes part of the permanent ledger. Let's talk about the two most widely used consensus mechanisms in blockchain: proof of work and proof of stake. While they serve the same purpose, validating transactions and securing the network, they work in fundamentally different ways. The proof of work flow involves several key steps that ensure the security and functionality of a blockchain network. Users initiate transactions on the network, such as sending cryptocurrency from one wallet to another. These transactions are broadcast to the network, awaiting validation. Unconfirmed transactions are collected into a mempool, memory pool, or temporary storage. TXCT.io provides a great visualization of transaction flow. Here, transactions are represented as people waiting for a bus, where blocks are the buses. miners select transactions from the mempool, prioritize those with higher fees, and package them into a block. Miners compete to solve a cryptographic puzzle by finding a nonce, a value that, when combined with the block's data, produces a hash matching specific criteria, for example, starting with a certain number of zeros. This process involves billions of guesses and requires significant computational effort. Once a miner finds the correct nonce, they broadcast their solution to the network. Other miners verify the hash to ensure it meets the required criteria. The validated block is added to the blockchain, linking it to the previous block by including its hash. This creates the chain in blockchain, ensuring the continuity and integrity of the ledger. The miner who successfully solves the puzzle is rewarded with newly minted cryptocurrency. It's called block reward, and transaction fees from the included transactions. The updated blockchain is propagated across the network. Nodes or network participants update their local copy of the blockchain to reflect the newly added block. And the process starts again as miners begin working on the next block. In proof of work, miners use powerful hardware to solve these puzzles, which ensures that creating a valid block is costly and tamper-resistant. The work in proof of work refers to the immense computational effort miners expend. Proof of work is a proven technology used by Bitcoin, which we'll talk about later in the video. But it surely has its weaknesses, requiring massive amounts of electricity. Validating transactions takes longer due to the competition. Miners need specialized, expensive equipment. Proof of work is highly secure due to its computational demands. For a bad actor to attack the network, for example, perform a 51% attack, to learn more about the attacks, check this video, they would need to control over 50% of the network's mining power, a virtually impossible task for larger networks like Bitcoin. For example, as of December 2024, Bitcoin's annual energy consumption was estimated at 169.7 terawatt hours, more than entire countries like Poland. Think of a proof of work like a massive lottery system. Miners buy tickets by expending energy. The more tickets they buy, the higher their chances of solving the puzzle and winning the reward. While this ensures fairness and security, it also results in significant environmental costs. While proof of work has been a cornerstone of blockchain technology, its drawbacks have led to the development of alternative consensus mechanisms, like proof of stake. Proof of stake focuses on securing the blockchain and validating transactions without relying on energy-intensive mining. Instead, participants stake their cryptocurrency to be selected as validators. In the next section, we'll explore how proof of stake works and how it addresses some of the proof of work's key limitations. And now I will give you a second to click the like button and subscribe. Users initiate transactions such as sending cryptocurrency. These transactions are broadcast to the network and placed in a mempool awaiting validation. Validators log up a certain amount of cryptocurrency as collateral, called their stake. Collateral is the cryptocurrency provided as security to ensure honest behavior. If the validator acts maliciously, some or all of the stake can be taken as a penalty. This process is known as slashing. A validator is chosen based on factors like stake amount, meaning that validators with larger stakes are more likely to be selected. To prevent wealthier validators from dominating, randomness or other fairness mechanisms are used. Some proof-of-stake systems also consider validator age, how long they've been staking, or reputation in the network. The selected validator proposes the next block by including transactions from the mempool. They ensure that the transactions are valid and comply with the protocol rules, such as preventing double spending. The validators, often referred to as attesters or witnesses, verify the proposed block. If the block is valid, they vote to approve it, using their staked cryptocurrency as assurance. Once enough validators approve the block, it is added to the blockchain. This process is faster and more energy efficient than proof of work, since it doesn't rely on solving complex puzzles. Validators who propose or verify valid blocks earn rewards, typically in the form of transaction fees or newly minted cryptocurrency. Rewards are proportional to the validator's stake and participation in the network. Validators that act dishonestly or attempt to add invalid transactions are penalized through slashing, meaning a portion or sometimes all of their staked cryptocurrency is confiscated, discouraging malicious behavior and ensuring network security. Proof of stake emphasizing financial commitment over computational effort. Validators lock their cryptocurrency as collateral, stay online, and are selected to validate transactions and propose blocks. This method maintains blockchain security while being more eco-friendly and scalable compared to proof of work. So, going back to the lottery analogy, proof of work is a lottery where you have to solve a puzzle to buy a ticket and only the fastest person gets the chance to win. Proof of stake is a lottery where your chances of winning are proportional to how much money you're willing to lock as a deposit. Both proof of work and proof of stake aim to keep the blockchain secure and decentralized, but they achieve this in very different ways. While proof of work is a proven battle-tested mechanism, proof of stake offers a more sustainable, scalable alternative, making it increasingly popular for modern blockchain networks. We've just talked about how blockchains use consensus mechanisms like proof of work and proof of stake to maintain security and achieve agreement among participants. But who are these participants and how do they interact with the network? This is where nodes come in. Nodes are the devices, computers or programs that connect to the blockchain, verify transactions, and store copies of the ledger. They are the backbone of the blockchain network, each playing a specific role to keep the system functional, decentralized, and secure. Let's explore the main types of nodes, and to make it more fun, I came up with this gym analogy. Just like a receptionist gives you the gym's layout and connects you to trainers or other stuff, a boot node helps new nodes join the blockchain by sharing information about active peers. Boot nodes are typically hard-coded into the blockchain client software and only play a role during the initial connection phase. They don't perform regular functions like transaction validation or block proposal. Full node, the gym manager, who ensures the gym operates smoothly by maintaining the current list of all members and tracking all ongoing activities. Full nodes store the entire current state of the blockchain and the most recent transactions, allowing them to independently validate transactions and blocks. Archive node, the veteran gym member. This is the guy who's been going to the gym since the day it opened. He knows every workout routine, every coach, and every member's personal bests. He keeps meticulous records of everything that has ever happened in the gym, even details others may no longer care about. Archive nodes are critical as they store the entire history of the blockchain, including all past states of accounts and smart contracts. They provide access to all the data that full nodes discard after validation. This makes them essential for applications like blockchain explorers or analytics platforms. But their high storage requirements make them less common than full nodes. The role of the trainer plays remote procedure call or RPC node, which guides GEM users through their specific needs. RPC nodes act as intermediaries between the blockchain and its users, helping users interact with the network. Whether you're checking an account balance, submitting a transaction, or querying contract data, RPC nodes process these requests. By offloading query and transaction handling responsibilities from validators, RPC nodes improve network efficiency and scalability. Lightnode, the remote GEM member who participates in the GEM but doesn't visit in person, watching workouts online and occasionally consulting the trainers for more detailed guidance. Light nodes or light clients store only a subset of blockchain data, usually just the block headers, to verify transaction authenticity without storing the full ledger, as they rely on full or archive nodes for complete data when needed. This lightweight design makes them perfect for mobile devices or low-powered computer. And finally, here they are, the consensus-making nodes we've learned so much about earlier, miners and validators. Miner node, the hardcore GEM competitor who trains intensively and competes in high-stakes events to win prizes and prove their strength. Miner nodes solve complex problems to add blocks to the blockchain and earn rewards, similar to athletes competing for trophies. Validator node, the fitness judge. Validator nodes confirm the validity of transactions and blocks, just as judge ensures the rules are followed and the competition remains fair. Now, when you've met the operators of the blockchain network who run the blockchain software, it's time to explore the role of the users. Users are the consumers who interact with the blockchain to find value in its services. They initiate transactions, deploy smart contracts, or use decentralized applications, or dApps. Unlike operators, users do not contribute to maintaining the network, but pay fees to access the services. These fees compensate operations for their work and help sustain the blockchain ecosystem. Together, operators and users form the backbone of the blockchain network. Operators keep the system function decentralized and secure, while users drive demand for the network's utility. And a user's journey begins with an understanding of the vital concepts of accounts and ownership in blockchain. Accounts are the way the system identifies ownership of assets or data. Think of an account as your digital identity in the network. Instead of relying on usernames and passwords, blockchain uses asymmetric cryptography to secure accounts. Here I need to mention what symmetric cryptography or encryption is to compare. So, symmetric encryption means that all participants must start with the same secret key, which is then used to secure communication. This shared secret allows them to exchange information safely, but if someone else discovers it, security is compromised. Like the famous case of the Enigma cipher in World War II, or nowadays example of a key locker for an Airbnb apartment, where the host and guests use the same code to access the key. If the code isn't changed, unwanted people could gain entry. Similarly, a building entrance with a changing password follows the same logic. Residents share a secret code to enter, but if it is used for too long, outsiders might figure it out. This is why encryption keys, like passwords, need to be updated periodically to maintain security. Asymmetric cryptography creates a public key from a private key in a way that ensures the private key remains secret. the private key acts like a secret password, allowing the owner to sign transactions and prove control over an account, while the public key serves as a publicly visible identifier, similar to a bank account number. Since public keys are long and complex, they are often converted into a public address which can be shared for receiving cryptocurrency or interacting with an account. Additionally, asymmetric cryptography allows people to encrypt messages using the public key, ensuring that only the private key holder can decrypt them, and to digitally sign messages with the private key so others can verify authenticity using the public key, proving ownership without revealing the secret. Additionally, zero-knowledge proofs extend this idea by allowing someone to prove they know a secret, such as a private key or password, without revealing any information about it. For instance, to prove I know the combination to a locked safe, which represents a system that requires proof of knowledge, like verifying a private key, without actually opening it. Someone slides a secret note inside, which only a person who knows the combination can access. And I open the safe and read the note without actually revealing the combination itself. In blockchain, ZK proofs are used in privacy-preserving transactions, identity verifications, and authentication without revealing sensitive information. It's important to understand that your private key is your most sensitive piece of information. It's a long string of alphanumeric characters that must never be shared. It allows you to sign transactions, essentially proving that you are the rightful owner of the account. If someone gains access to your private key, they can control your funds and perform transactions without your permission, while public key is used to verify transactions signed by the private key and can be safely shared with others. It is derived mathematically from your private key, but cannot be reversed to reveal it. Encryption is the backbone of blockchain security. When you sign a transaction with your private key, encryption ensures that only matching public key can verify it. This guarantees that the transaction is authentic and originated from the account owner. And the asymmetric nature of the encryption means your private key is never exposed or shared, even during transaction verification. In case you lose access to your private key, you can recover it with the seed phrase that was provided when you've created your account in the wallet. This secret recovery phrase is a human-readable backup of your private key, usually of a series of 12 or 24 words. And this seed phrase must be kept secure even better than the private key, as anyone with access to it can regenerate your private key and take control of your assets. Now that we've discussed accounts and cryptographic ownership, you might wonder, how do users manage their private keys and interact with their blockchain accounts? This is where crypto wallets come into play. A crypto wallet is a tool that helps you manage your private and public keys, interact with the blockchain, and access your funds. Wallets don't store cryptocurrency directly, but provide access to the blockchain accounts where the funds are stored. Crypto wallets fulfill mainly three functions. Wallets generate and store private keys securely while deriving public addresses from them. When a user initiates a transaction, the wallet signs it with a private key before broadcasting it to the blockchain. Wallets communicate with blockchain networks, often via RPC nodes, to send transactions, query balances, and interact with dApps. There are two main types of wallets based on how they store keys and connect to the blockchain. Hot wallets, always connected to the internet, convenient for daily use but less secure. cold wallets stored offline, offering high security for long-term storage. So having an account means there's infrastructure to use it. But what is Web3 and how does it differ from the previous versions? With the rise of the internet, static websites emerged, where users could only read information but had little to no interaction. For example, personal blogs, online directories, etc. While always-on servers became common, interactions were still largely peer-to-peer, and cryptography was used but not widespread. Web 2, the interactive social web that we use today. Platforms like Facebook, Twitter or X, and YouTube allow users to create, share, and engage with content, but these platforms are centralized, controlled by a few corporations that manage data, algorithms, and monetization. Users must trust these providers to store and manage their data correctly, but companies can censor content, restrict access, and modify stored information without transparency. While Web3 is a decentralized internet built on blockchain technology, smart contracts, and decentralized applications. Unlike Web 2, where users rely on central service providers, Web3 enables trustless interactions, where cryptographic proofs and economic incentives ensure honesty. Users control their own data and services operate transparently without a central authority. This allows for shared state, open governance, and new applications models where users interact with the system without intermediaries. Blockchain is the infrastructure powering Web3, while Web3 envisions how this infrastructure can transform the internet into a user-centric and decentralized experience. Think of blockchain as the engine and Web3 as the car that uses this engine to create a new driving experience. Web3 began with Bitcoin in 2009, created by the enigmatic Satoshi Nakamoto. Unlike traditional organizations, Bitcoin has no CEO, no headquarters, and no single entity in control. This anonymity aligns with Bitcoin's ethos of decentralization, ensuring no central figure could influence or compromise the system. Satoshi Nakamoto disappeared from public communication in late 2010, leaving the project in the hands of the community. To this day, Satoshi Bitcoin wallet containing over 1 million BTC remains untouched, adding to the mystery. Could one person truly create Bitcoin? What are your thoughts? While the idea was groundbreaking, its underlying technology was built on established concepts like cryptographic hashing, digital signatures, and distributed systems. It's theoretically possible for one highly skilled person to have created Bitcoin, but many believe it was likely the work of a small, highly skilled and coordinated group. Bitcoin is entirely decentralized, with decisions about its development made collectively by the global community. Designed as a peer-to-peer electronic cash system, Bitcoin enables people to send and receive money directly anywhere in the world at any time without relying on intermediaries like banks. The very first Bitcoin block, Genesis block as we know, contained the embedded text.
The Times, the 3rd of January 2009, Chancellor on brink of second bailout for banks.
This message referenced the headline from the Times newspaper on the day the block was minted, hinting at Bitcoin's mission to provide an alternative to traditional financial system, especially in the wake of the 2008 global financial crisis. The true innovation behind Bitcoin lies in its blockchain technology, a decentralized, immutable, and transparent ledger that solved the problem of double spending. Bitcoin also introduced the proof-of-work consensus mechanism, where miners validate transactions and secure the network, earning Bitcoin rewards in the process. One of the Bitcoin's defining features is its 10-minute block time, carefully chosen to balance security, decentralization, and stability. This interval allows time for blocks to synchronize across the global network, reducing the risks of forks and double-spending attacks. To maintain this interval, the network automatically adjusts its mining difficulty every 2 weeks, ensuring consistent block production regardless of changes in the numbers of miners or computing power. Now a fun fact. The first real-world Bitcoin transaction took place in 2010 when programmer
Laszlo Hanich
paid 10,000 Bitcoins for 2 Papa John's pizzas. Today those pizzas would be worth over $1 billion. This milestone is celebrated annually on Bitcoin Pizza Day on 22nd of May as a reminder of Bitcoin's humble beginners and its journey towards mainstream adoption. One of the reasons for such a drastic price growth lays in Bitcoin's capped supply of 21 million coins, which ensures digital scarcity much like precious metals. Its value is further enhanced by a mechanism called halving, which reduces the mining rewards by half every 210,000 blocks, roughly every 4 years. When Bitcoin launched in 2009, miners earned 50 BTC per block. Today, the reward is 3.125 BTC, and the last Bitcoin is expected to be mined around 2140. This combination of limited supply and decreasing insurance has established Bitcoin as a store of value, often referred to as digital gold. Why is Bitcoin legendary? As the original cryptocurrency, Bitcoin defined blockchain technology and remains the most trusted digital asset. Its limited supply and scarcity make it a hedge against inflation, preserving value over time. Despite market crashes, regulatory challenges, and competing innovations, Bitcoin has proven its durability. Its global network of nodes and miners ensures unparalleled decentralization and resistance to tampering. Halvings, mining difficulty adjustments, and transaction fees create a carefully balanced economic model. Bitcoin's influence has grown significantly over the years. Major companies now accept it as payment, add it to their balance sheets, and offer Bitcoin-based financial products. Some countries, like El Salvador, have even recognized it as an official currency. Although Bitcoin's primary purpose is transferring and storing value, its impact goes far beyond. By introducing a decentralized, trustless system, Bitcoin paved the way for platforms like Ethereum to build on its foundation and expand blockchain's possibilities. Before Ethereum, there were indeed Bitcoin forks or alternative cryptocurrencies, altcoins, that emerged. The primary use of these early cryptocurrencies was for token transfers, sending coins from one address to another, and trading on various exchanges. There wasn't much beyond this in terms of functionality, and the concept of using blockchain for anything beyond simple transactions was not widely implemented or even considered by many. However, the Bitcoin community was already vibrant, discussing and debating various aspects of cryptocurrency, including scalability, governance, and the philosophy of decentralization. While Bitcoin introduced the world of blockchain, Ethereum revolutionized it, launched in 2015 by Vitalik Buterin and his team. Ethereum expanded blockchain capabilities beyond currency by introducing smart contracts. Smart contracts are self-executing agreements with the terms directly written into code, enabling automation and trustless interactions. More about smart contracts you can find in this video. Interesting fact. On 15th of September 2022, Ethereum transitioned from proof of work to proof of stake. This complex process required precise coordination to maintain the network's security and functionality during the transition. Known as the merge, it stands as one of the most significant events in Ethereum's history. Ethereum's innovation allowed developers to build decentralized applications on its platform. These dApps operate on the blockchain, offering transparency, security, and censorship resistance. Ethereum introduced the concept of programmable money and gave rise to entirely new industries like decentralized finance, DeFi, and non-fungible tokens, NFTs. However, Ethereum's rapid growth exposed scalability issues. As demand increased, so did transaction fees and network congestion. These limitations led to the rise of alternative blockchain platforms, such as Solana, designed to address these challenges. Solana entered the blockchain space in 2020 with a mission to tackle the scalability and speed issues that plagued earlier platforms. Solana's founder, Anatoly Yakovenko, introduced a unique feature to proof of stake, proof of history, which timestamps transactions before they're processed. This innovation allows Solana to achieve extremely high throughput, capable of processing up to 65,000 transactions per second, and maintain low fees. Solana's efficiency has made it a popular choice for applications requiring high-speed transactions such as decentralized exchanges and NFT marketplaces. It has also attracted developers and users looking for a seamless experience without the high costs associated with Ethereum. While still in its early stages compared to Bitcoin and Ethereum, Solana's focus on scalability and user experience positions it as a key player in Web3 space. Web3 has grown into a vibrant ecosystem with countless projects and platforms pushing the boundaries of what's possible with blockchain technology. As Web3 continues to grow, its ecosystems are becoming increasingly diverse, encompassing finance, art, governance, gaming, and beyond. Each project and platform contributes to a decentralized future where power and ownership shift back to users. Together, they form a new internet, one that is decentralized, user-centric, and full of possibilities. Thanks for watching. Bye.